In this lesson, we will examine some common types of pumps, compressors, and motors. The generic expression used to describe a device which develops flow will be a flow generator, and a device that receives flow and produces mechanical energy as a flow receiver. We examine only basic types in the unit, but it should be understood that all flow generators produce flow in the same way. Likewise, all flow receivers produce mechanical energy in the same way. The amount of power a system can produce is limited by two main factors: flow rate and pressure. As in electricity, power is calculated by multiplying voltage and current. In fluid power systems, we multiply pressure and flow rate. No matter what design of pump or compressor is being discussed, all pumps produce flow the same way. Pumps and compressors produce flow by creating a pressure differential. Fluids always flow from a location of higher pressure to a location of lower pressure. By using the increasing pump volume at the inlet, the pump or compressor creates a region of decreasing inlet pressure, a vacuum, and this causes higher atmospheric pressure to push the fluid to the lower pressure location at the inlet. In this illustration, a piston moves from right to left, causing an increase in volume. This results in a decrease of pressure. The decrease of pressure causes a net difference between the pressure outside and inside of the pump at the inlet port. The fluid, as influenced by a greater value outside, is forced to the inside, filling the volume. Once filled, the piston moves back up the cylinder toward the ports, causing a decrease in volume and an increase in pressure. Motivated by a connection to a point of lower pressure, the outlet port, the fluid is displaced through the outlet port into the system toward the point of operation. If the pump is moving a liquid, the displacement is equal to the internal dimensions of the pump and is the same each time fluid is displaced. If the pump is pneumatic, a compressor, the displacement will be determined by a pressure and compression ratio, since gases compress. This is why pneumatic systems are not used in circumstances requiring tremendous forces. All pumps produce flow in the same way, regardless of their fluid type. The two main factors that determine pump or compressor flow are their physical size, measured in cubic inches per revolution, and speed in revolutions per minute, or RPM. Speed multiplied by volume gives you displacement per revolution. If calculating pump flow, it is common to multiply the displacement by the speed and divide it by 231, the number of cubic inches in a gallon, which produces an answer in gallons per minute, or GPM. There are pump designs which are not positive displacement. These types are called dynamic, meaning they add kinetic energy to the fluid to make it move. The method of flow generation is the same as I have already explained. There is generally a rotary group that begins to move, creating a difference in pressure between one side and the other. While this design would not be suitable for high pressure applications, they do produce large amounts of flow. Examples include distribution for lube oils and coolants, large volumes for blowers and vacuum units. The basis of hydraulic horsepower is pressure and flow rate. A relationship exists between these two quantities that produces a consistent relationship based on a rule that uses 1500 psi as its reference point. The rule of 1500, as it is known, is a ratio between input horsepower and flow based on a starting pressure of 1500 psi. For a system at this pressure, the input ratio of horsepower to flow is 1:1. For example, let's say you have a 5 GPM pump and use it with a system pressure of 1500 psi. It will take 5 horsepower to drive the pump against that pressure. This is a ballpark rule of thumb. A closer calculation may be made with a horsepower formula, which is pressure multiplied by flow divided by 1714. This formula does not take into account the mechanical efficiencies of a pump. A similar formula is used for air compressors, but I have chosen not to discuss it in this course. These are the basic symbols for flow generators. They are identical except for one thing. A hydraulic pump has an arrow colored in. A compressor has an arrow which has no color. Note that the arrows are pointing out because they are producing flow, and we call them flow generators. Gear pumps were the mainstay of the hydraulic industry for many years. They are cheap to manufacture, work well in multiple environments, and have decent service life when well maintained. They do, however, leak internally, and the leakage is aggravated by high pressure and wear. Leakage, or slippage as it is sometimes called, is the oil leaking past the tiny clearances that exist between the moving parts, including the gear faces. Note the direction of rotation. On the left side of the illustration, space is increased as the teeth move away from one another. Space is decreased as teeth move toward one another on the right side, and oil is forced out into the system. The next pump we will discuss is the vane pump. This is a photograph of the internal rotating group of the vane pump. The major parts are the rotor, the vanes that are slotted into the rotor, and the outer part called the cam ring. Vane pumps are well known for their long service life and efficiency. Since the vanes rely on centrifugal force to seat against the cam ring, these pumps require running speeds at or above 600 revolutions per minute. In this cross-sectional illustration of a vane pump, color is used to identify different pressures. The green is low pressure, located at the inlet port, and the red is high pressure near the outlet port. The group rotates clockwise. As the rotor spins, centrifugal force pulls the vanes against the inside of the cam ring and form a seal. The cam ring is stationary, while the rotor is connected to and driven by the prime mover. Notice that as the rotor and vanes move, an increasing volume is exposed to low pressure up to about 180 degrees of rotation. After 180 degrees of rotation, the spaces get smaller and the oil is forced out into the system. First, notice that in this picture the cam ring is elliptical. Manufacturers designed this kind of vane pump to be balanced around its rotor. The way they do this is to separate the low pressure side and the high pressure side into 4 different pressure quadrants. With 2 low pressure and 2 high pressure ports located at about 90 degrees apart, the load on the bearings is equalized, helping the vane pump to achieve one of the longest service lives of any design. Many manufacturers of these types of pumps make available a service kit called a cartridge assembly, which essentially replaces all of the worn parts of a vane pump, and they are quick to install. Some pumps can change their output by making adjustments to the rotating group. In the variable volume vane pump, the rotor spins but remains in the same location on its axis. The cam ring slides from side to side. When the cam ring is positioned so as to place the rotor at its center, the pump produces no flow because the displacement does not change in this position. The position of the cam ring can be adjusted by an external control or by a spring, as in the next slide. In this illustration, the cam ring is understood to move when the adjustment screw is turned. When a spring is used to offset the cam ring, the function is called pressure compensation. In this illustration, the pressure from the system pushes back on the cam ring, which in turn pushes back on the screw adjustment or a spring. When the tension of the spring is reached, the rotor is centered and flow stops. In this way, system pressure is controlled by the spring on the cam ring. If the spring tension is adjusted, the pressure of the system and stoppage of flow is affected. Pressure compensated pumps can be piston type or vane type. The gear pump cannot be made variable displacement unless its speed is changed. The schematic symbol does not tell the reader which type of pump they are looking at, only its function. Due to greater internal lubrication of moving parts, these kinds of pumps and motors require that the case be constantly drained in order to prevent internal pressure buildup, which could damage the shaft seal. Whenever a pump is replaced, it's always a good idea to check this drain line for blockage. In this illustration, the schematic symbol for a pressure compensated hydraulic pump is shown. Notice the arrow in the box that points straight up. This arrow is distinct from the one that crosses the symbol diagonally and indicates variable volume. All pressure compensated pumps are variable volume. This picture is of a double vane pump. When both groups are working together, flow is at its greatest. If the larger one is isolated, flow is reduced to the displacement of the smaller group. This may be done to slow the approach of an actuator, such as a feed rate to a workpiece or point of operation, to prevent machine damage. This is the schematic symbol for a double pump and identifies the difference between the sizes of each group. The vertical lines are inlet and the outlet ports. The horizontal lines are the drive shafts. The piston pump is known for its high efficiency, the highest of any pump, and durability in high pressure systems. This is a section cutaway for an axial piston pump. This pump gets its name from the fact that the pistons move in parallel to the drive shaft axis. Pistons are contained in a barrel that spins. The barrel is splined to the drive shaft, which in turn is driven by the prime mover. The pistons are forced to move back and forth within the barrel as it rotates. The position is controlled by the shoe plates. As the pistons move forward, the fluid is displaced, and as they move back, fluid is drawn into the barrel. A port plate is connected to the inlet and outlet ports. There are no seals on these pistons, only a tiny clearance which is filled by lubricating oil. The swash plate in this model is fixed and at set angle. The pump is fixed displacement. An exploded view of the internal group shows the pistons with shoes that slide on the swash plate. The shoe plate maintains contact between the piston shoes and the swash plate. The barrel and pistons are prevented from excessive movement by the bias spring, which ensure the barrel stay firmly against the shoe plate. These parts are often sold as a unit for servicing this kind of pump. Almost every manufacturer of these pumps uses the same kinds of parts. This illustration is a cutaway view of a pressure compensated piston pump. Its volumetric output is controlled by the angle of the swash plate. Swash plate angle is controlled by a spring which pushes the swash plate to full flow at low pressure. When pressure builds, the small piston shown right above the barrel forces the swash plate back to the vertical position where no flow is produced. This slide provides a better view of how the compensator works on the swash plate to control flow. On the left side, the system is understood to be at low pressure. At low pressure, the bias spring pushes the swash plate to maximum angle. As pressure builds, the compensator piston pushes the swash plate against the stop where it is vertical. In this position, the pistons are no longer able to move back and forth, preventing displacement, and no oil is being moved. The pistons in a radial piston pump move at 90 degrees to the drive shaft axis. These kinds of pumps are compact in size, have quiet operation, and are often used in mobile hydraulic applications. The most common design uses a cam to push the pistons in order to produce flow. Check valves ensure oil is moving in the correct direction. They are efficient at multiple speeds and high pressures. These are different styles of these pumps, and the same designs are also used as motors. Sometimes hydraulic pumps are used as transmissions for mobile equipment. When this is the case, a forward and reverse direction is needed. An over-center pump provides two directions of flow. Piston pumps are often used for this purpose, which provide two directions of fluid movement accomplished by a swash plate which can move from one tilted extreme to the center position and to an opposite tilted extreme. Control may be provided by an external mechanical device. Compressors provide airflow for pneumatic systems. There are many different types, but their operating principles are the same. We will discuss the more common types in this presentation. This picture is that of a screw-type compressor. We will discuss it in more detail later. This chart breaks down compressors into two main categories. Compressors that add kinetic energy to the air to generate flow are called dynamic compressors. They are non-positive displacement, but function in much the same way as a house fan does. Compressors that trap the air and force it to move are displacement compressors. For an example of a dynamic compressor, examine a turbocharger used on an engine. An example of a displacement compressor would be a piston compressor. Dynamic compressors typically use a rotary member that resembles a fan blade. The blades are pitched and when moving create differences of pressure between one side and the other. A very tiny difference in pressure is all that is needed to create flow. The most common compressor in use today is the reciprocating piston compressor. Although this illustration shows a compressor with mechanical valves, it should be pointed out that most compressors of this type use a plate valve similar to a reed valve found in two-cycle engines. As the piston moves down, air is drawn into the cylinder chamber. As the piston moves upward, air is directed out through the exhaust valve and toward the receiver tank. As the air is compressed, it gets hot because energy was required to compress it. This energy is transformed into heat and is not usable for doing work. In the pneumatic system, the greatest amount of heat and wasted energy occurs at the compressor. To make matters worse, when the heated air gets to the receiver tank, it loses temperature and pressure and aggravates the already poor efficiency of the system. The explanation to this is found in Charles' law. Designers have a means to reduce this loss. Compressed air systems become more efficient when the temperature losses in the receiver tank are minimized. One way to accomplish this is to compress the air in multiple stages and removing some heat before the air enters the receiver tank. Air is compressed first in a larger stage and then sent through a heat exchanger called an intercooler. Remember that heat will transfer to any surface with less heat. This is how the intercooler works. In the intercooler, heat is transferred through the walls of the intercooler into the airstream that blows over the intercooler as provided by a fan. As air enters the second smaller stage, it is already at a reduced temperature but a higher pressure. It is at this second stage that the air is compressed further, providing higher pressures at lower temperatures. Lower temperatures mean less loss of energy due to heat dissipation. This picture is that of a screw compressor. When it comes to maintenance costs, rotary screw compressors have an advantage over reciprocating compressors. Double-acting reciprocating compressors typically require more periodic maintenance than rotary screws. Valves, piston rings, and other consumables on a reciprocating compressor need expensive routine maintenance. Rotary screw air compressors are displacement compressors and are the most common types of compressors used for industrial applications requiring over 30 horsepower. Air comes in through a valve, typically called the inlet valve, and is taken into the space between the rotors. As the screws turn, They reduce the volume of the air, thus increasing the pressure. There are rotary screw air compressors with just one screw as well. Air oil separators work according to the principle of coalescence. Microglass fiber layers separate drops of oil from the compressed air and return them in large drops to the oil circuit of the compressor. The separation process is effective enough to reduce particle size to the sub-micron range, particles less than a micron in size. This ensures that oil consumption in the compressor and oil entrainment into the compressed air network are kept to a minimum. Oil vapor is not separated. Air-oil separators can be used with all types of standard compressor lubricating oils, no matter whether they are mineral-based, synthetic, or partially synthetic. Fluid power motors, as well as cylinders, are flow receivers. Whether hydraulic or pneumatic, the operating principle is the same. Fluid enters the inlet port under pressure and then contacts the rotating group. The pressurized fluid forces the group out of its way in order to reach a point of less resistance and then exits the motor at the outlet port. Pneumatic motors often have a muffler attached to the outlet port to reduce noise. The basic symbols show the arrows pointing inward. This device receives flow and produces rotary force for mechanical energy. The amount of force is proportional to the motor's physical displacement and the applied pressure. In this animation of a gear motor, fluid enters on the left and contacts the gear faces, causing them to move away from and separate from each other. As the gear faces separate, they cause rotation, which is delivered to an external shaft, and mechanical rotary force is produced. This force may be calculated and requires the pressure value and the size of the motor in cubic inches per revolution. This slide shows three common types of motors. These are not the only ones, but every motor operates by the same principles. An understanding of these principles may be applied to every design to explain their operation. Torque is a twisting or turning effort, which is measured in units of inch-pounds for Fords and foot-pounds for Chevys. Actually, the unit of inch-pounds is most common for fluid power motors. All that is needed is a system pressure and the size of the motor in cubic inches per revolution. If a motor whose displacement measures 0.203 cubic inches per revolution is subjected to a pressure of 500 psi, it will produce 16.16 inch-pounds of torque. For the exact formula, see Appendix B of your lab manual. The actual torque a motor will produce is based on the amount of load on its shaft. No matter what the system pressure is, the motor will generate only the torque needed to overcome the resistance to its group and its shaft. Resistance to shaft rotation comes from many different sources, and they occasionally need consideration. These values are starting torque and running torque. A popular motor design for low-speed, high-torque applications is the gerotor, also known as the roller stator. In this illustration, you can see the two main internal components, but its operation is different from that of other designs we've looked at. The centerpiece rotates around the inside of the outer piece. This is why the motors are known for their distinct clicking noise as they operate.